So as a summary, in order to understand what is happening intuitively, so your input signal, you multiply by your sampler. So sometimes we denote this part as we put it a switch using like MOSFET, and then we put T equal to NTS, and then you have X of T, and here you have X of NTS. Okay, but this signal, the sample signal, is also a continuous time which contains only XNTS. Okay, so this is what we have. And then if you want to reconstruct it, we give it back to our sinc filter, and then we get our reconstruction filter. So this is the impulse response of this system, and X hat could be that. This is what sampling theorem says. But let's look at a curve in time domain. Suppose that this is xt, this is the signal that you have it. And what happens is that when you multiply by this pulse train is at time minus t, you multiply it by a delta, here you multiply by another delta, you take samples at this point. So you take this value, this value, which is happens to be 0, this value at 0, this one, this one, this one, this one, and this one. Using these values, I shall be able to calculate the value of my signal at any other process at this point and any point like that. So the sample signal XST is the red signals. So these red signals are my sample signals, because I have a summation here, okay, which is the red signals, which is 0 outside of in between and just impulses there. When you give these to your reconstruction filter, what happens is that this delta is replaced by this sinc function. So you will have, for instance, if n equals 0, you will have a sinc at time t is 0. So you multiply this height and then you replace it by a sinc value. So for n equals 0, you will have this signal. For, let's say, n equal minus 5, you will have a sinc like that. Minus 4, you will have this sinc. For minus 2, you will have this sinc. Minus 1, you will have this sinc. And then you will have, for 5, you will have this one. And different samples, they give you different sinc values, okay? Now, if you add these sinc functions, if I add, let's say, all these values that I have here, or this value, at the integer time multiple factor of ts, for instance, at this point, all these sinc functions are 0 except the green one. At this one, all of them are 0 except the brown one. So at the multiple integer values of ts, I will get the exact value of my signal. And in between, I get the summation of those sinc components, which give me these nice and smooth functions. So the reconstructed signal becomes exactly equal to this one if the number of samples are enough, if my curve is smooth enough that this sinc interpolator could reconstruct it. So this is the meaning of sampling theorem. So this very beautiful theorem, which has been the basis of the development of technology, is just theory, because it's not causal. Because if you go back, look at here at this summation, you need to have a summation from minus infinity to plus infinity, and it's not causal. So these beautiful theorems not only give you the mathematical theorem, but it says that I'm not practical, I have practical limitations, and also it gives you how you could approximate it and what is your error approximation, and how to use it as best. For instance, it says that the generation of perfect impulses. So you cannot generate perfect impulses in order to reconstruct your signal. So you approximate it. So instead of a delta Kronecker signals, which is like pulses like that, okay? So you could generate like RC circuit and have exponential, provided that this is small enough, okay? Compared with your bandwidth, you could overcome these, but you will have some errors. causality of the sync interpolator. So causality you could overcome by accepting some delays, a couple of samples, 2, 3, 4, 5 samples of delay will allow you almost perfectly reconstruct. So again, as a summary, so I have a continuous time signal. If I transform it in frequency domain, provided that my component of signal above W and below minus W or 0, I call it band limited signal. Then I multiply these by my pulse train, and the Fourier transform of this one, so this is a Fourier transform, and Fourier transform of these is also a pulse train. Because you multiply these signal by these signal, you get your samples. Here you have to convolve them, so your convolution, when you do convolve it, then that means that this one will be convolved with this one, gives you this pulse. This one, when you convolve it with this one, it means that you get this signal shifted and a replica will happen here. This one will be convolved with this one, it will be shifted and will be replicated here. If you want to get your signal back, provided that this replica and this replica, they don't have any overlap, it means that I have full information about this shape, and by applying a just ideal filter here, I could eliminate those one and then preserve this one and get it back. So this is the basic idea of sampling theorem.